from ETH, who will tell us about the self-section of the Torelli map. No.
The Taylor expansion of the Torelli map and its applications to section theory.
Okay.
So we're going with this talk about the Taylor expansion of the Torelli map at the boundary and how you can use it as a tool to study cycles on the moduli space of abelian varieties. So the Torelli map relates both topics of this conference, which are the curves and abelian varieties, and it goes from the moduli space of curves of compact type. These are the curves inside MG bar, such that the nodes are separating, and it maps to the moduli space of principally polarized abelian varieties. And it takes a curve and maps it to its Jacobian that parameterizes line bundles that have degree 0 on every component. And when the curve decomposes into its irreducible components, Ci, then the Jacobian will decompose as a product of the Jacobians of the irreducible components. So conveniently, AG, since I will be working over C all the time, AG can be written as a quotient by a space of complex matrices modulo a group action. And this is a space, Siegel upper half space, which parameterizes complex G by G symmetric matrices with positive definite imaginary part. And the Torelli map also has an analytic description. So it associates instead to a curve its period matrix. So first you take a symplectic basis for the homology of the curve, the first homology. And then you take a basis of differential homomorphic differentials on the curve that are dual to the alpha cycles. Meaning that the integrals of these differentials over the alpha cycles are equal to the contour delta symbol. And in this, using this description, the Torelli map associates to a curve, its period matrix inside the Siegel upper half space, which has entries given by integrals of these homomorphic differentials over the beta cycles. So what can we say about the Torelli map? So first, the Torelli map is proper. Which means that we can push forward cycles to AG from the space of compact curves. And then secondly, if we look at the smooth locus of the curves that are smooth, then because of the Torelli's theorem, a curve is completely determined by its Jacobian, so it's injective on geometric points. On the other hand, if you also remember the automorphisms, you have to take into account that a generic Jacobian has two automorphisms given by the sign involution and the identity, whereas the curve only has one, so then it's actually 2 to 1 as stacks, and we're going to work with the stacks. But then, on the other hand, when you look at the boundary, the injectivity is completely destroyed because the Torelli map forgets how various components are glued together. So the Jacobian of two curves C1 and C2 glued together at points P and Q will be the same as the Jacobian of the same curves glued together at different points. So when G is greater than 2, this means that we get positive dimensional fibers. And if we compare the dimensions of both sides, we know that the dimension of the modular space of curves is 3G minus 3, whereas the dimension of AG is the same as the dimension of the space of symmetric G by G matrices. So it's the G triangular number G times G is 1, 2. Okay, so some questions that I've been studying lately is to try to compute some scheme structures involving the Torelli map, and more specifically, of some fiber products involving the Torelli map, and more specifically, the fiber products I've been studying is to, how to calculate. So specifically, I've been studying the fiber products of the Torelli map with itself, which is related to the title that Sam gave me in the beginning. But then I've also been studying the fiber product of the Torelli map with the locus of abelian varieties that can be decomposed into a product of smaller dimensional abelian varieties. And then lastly, recently, I've also been looking at a different fiber product that instead involves the prim map, but you can apply similar strategies to try to find a scheme structure. And here, this is the extended modular space of prim varieties constructed by Beauville so that this map is proper. And here, the sum of the g i's equal to g minus 1, and here the equal to g. And the map pi here is a product map that sends a tuple of k smaller abelian varieties to the product. Okay, so why am I studying this fiber product, the scheme structure? So the motivation is to do some intersection theory calculations on AG. And more in these cases, we're interested in calculating pullbacks of cycles under the Torelli map. T. And so the pullback of the Torelli cycle and the pullback of the locus of decomposable abelian varieties. And also you can try to pull back the product locus under the prim map. And this would be using excess intersection theory on the spaces x, y, and z. So the way excess intersection theory works is that to compute a cycle-theoretic intersection, we first look at the geometric intersection of the cycles. And if this space has, it can be decomposed into various distinct smooth components of the right dimension, then the intersection class would just be the fundamental classes of this thing itself. But on the other hand, if the geometric intersection has more dimension than the expected dimension, then it means that the intersection is not transverse, so that you have to cut down dimension by looking at the normal directions in which the intersection is not transverse, and then you take the top Chern class, which simulates some some perturbation in the excess bundle. But in order to calculate this intersection class, you need to understand the precise scheme structure of x, y, and z, and not just the geometric points. Because the intersection class will get contributions from the various components and from their intersections, and also if you have some non-reduced structure, you can get some contribution from there too. So in this case, I calculated the class for g equals 4. some non-reduced scheme structure to deal with. Whereas this case was a bit nicer. So, I mean, the case where k equals 2 and we have a1 times ag minus 1 was done by Canning, Priya, and van der Pan in 25. But now we have managed to extend it to do so that we can do the computation for all G1 up to GK, such as the sum is G, and using access intersection theory. And this is in a paper by 10 authors: Canning, Drakengren, Foisy, Holmes, Irbar Lopez, Nesterov, Priya, van der Pande, Schmidt, and Sun in 26. Everyone is here at the conference except for Holmes, because it's Daniel Holmes and not David Holmes. And in this paper we use 2 different methods to complete this class, and the method that involves the Fulton access intersection theory relies on knowing the precise scheme structure of Y, and this is something I proved in a separate paper in 26, that this fiber product Y is reduced. Okay, any questions so far?
How about the third case?
Oh, so that one we have not managed to compute because it turns out to be pretty complicated, but you can still try to understand the scheme structure here and see why it makes it a bit difficult to discuss.
So for A, this is like a very stacky issue.
It's very stacky. Yes, you have a lot of like automorphisms to take into account. So you can just so first you describe this map with like local coordinates, and then you have to take various different kinds of fiber product by applying some like involutions and get slightly different maps. Yeah. But in the second case, we don't have because of many automorphisms of the we don't have the same issues.
What about the other Noether-Lefschetz loci?
Sorry? Sorry, what about?
The other Noether-Lefschetz loci.
So the other Noether-Lefschetz loci, you can try to pull back the Noether-Lefschetz loci under the Torelli map. I haven't exactly figured out how to match up the local descriptions of the Torelli map with the local description of the Noether-Lefschetz, but that's something that you can try. Okay, so the strategy for finding these scheme structures in A, B, and C will be to describe the Torelli map and the pre-map and the product map in local coordinates. And the product map is going to be rather straightforward, whereas for the Torelli map and the pre-map, we need to use the description of the Torelli map as a map taking a curve to its period matrix, which corresponds to integrals of differentials over cycles, and then you want to extend differentials from a nodal curve to a neighborhood so that you can, and then expand them in local coordinates, and then integrate so that you can get an expansion of the period matrix in smoothing parameters. So for local coordinates, we start with the local coordinates inside MG compact type. So first you associate to the curve its dual graph, gamma c. And then the first set of coordinates you take will be coordinates that corresponds to deformations of C that remain of the same topological type. So these coordinates I denote by x. And I denote this locus of curves with the same topological type as M subscript gamma C. And then you also want to have some coordinates corresponding to deformations where you smooth out nodes of the nodal curves. And these are called plumbing coordinates. So each node, so each edge in the dual graph, you can associate a smoothing parameter. By a construction called plumbing. So the way this works is that you take an edge at a time, or you take an edge in the dual graph and you take an orientation. And let minus e be the opposite orientation. And you choose a value for the smoothing parameter. So then, when you have this curve C that you want to smoothen out, and these are the components that are the vertices at both sides of E. And here I denote the nodes by Q E and Q minus E on both curves, and I make a small loop around this node that has I label by gamma E, and it's the boundary of a disk in a local coordinate centered at this node and with radius.
The blue is not so easy to see.
Okay, I go with red. It's red better. Orange. Okay.
Yeah, that's better.
Okay, so it's the boundary. Blue and orange is also very cool together. Maybe that makes it less readable or more like. Okay, so now you want to smoothen this node out, and then you just cut out these small disks and you glue together the loops. Use my context again. Oh no, I glue them together, so I use the same color for both. And to get a holomorphic structure on these, you identify the loops via the map. That sends a local parameter around Q to S over the local parameter near Q and minus E. So ZE and Z minus E are local coordinates near QE and the Q minus E. And then you can do this for all edges in the dual graph, so that we obtain, for a given set of smoothing values for the smoothing parameters, you obtain a curve which is smoothed out accordingly. So that when you set S equals 0, you recover your original curve. So in this way, these smoothing parameters actually form coordinates for the moduli space of curves. And so now these were the coordinates for the curves, and let's now move to the coordinates for the moduli space of abelian varieties. So locally, since this Siegel upper half space is an analytic cover of AG, we can instead put coordinates on Siegel upper half space. So we can lift the Torelli map the prim map to the Siegel upper half space. So we pick coordinates for HG to correspond to the matrix entries of the matrices that this space parameterizes. symmetric G by G matrix. With possibly definite, symmetric with possibly definite imaginary part of entries given by these coordinates. And similarly, you can obtain coordinates for single upper half spaces of smaller dimensions so that you also get a set of coordinates for the product of HGIs for the smaller Gs.
These are coordinates for all things except for the moving the complex structure when you have fixed nodes. You haven't named those.
In this case, I've given you all, sorry, which coordinate did you say?
Ones is what you just said.
So X is a set of coordinates that remain the same close to that. You can also fix the homomorphic structure and keep the nodes, and these will also be included in the X coordinates.
So the full coordinates for the compact vector, the X's and then the S's.
And the S's, yes. Any other questions meanwhile? So now that we have these coordinates, we can start by describing the product map in these local coordinates. And the product map we can assume to be given by the map sending a tuple of, so it's mapped from HG1 up to HGK, mapping to HG, where this is the lifted product map, and it takes a tuple of matrices which are GI by GI, and it maps this to the big matrix that has the smaller ones in the block diagonal. Okay, so this was the part that's not so difficult. So the next task is to describe the Torelli map in local coordinates. So this will be done using a method of varying differentials under smoothings of curves. So what we want to do is we're given a curve inside MD compact type and a holomorphic differential that we want to vary. So for each set of values for the smoothing parameters, or for small values of the smoothing parameters, we want to construct a holomorphic differential on the smooth end curve CS. Such that when you put s equals to 0, you should recover the original differential omega. And remember that now our curve CS is something that we obtain by gluing together components associated to vertices of the dual graph by connecting some small disks. So then, at first, you can try to view this as a differential on this smoothed curve, but then you get a holomorphic differential which defined on the complement of the loop, but then has some jumps along this loop. So there's a paper by two previous PhD students of Sandruszewski, Norton and Hu, where they construct a differential or something that you can add to each of these parts so that you cancel out this jump. So a paper by Hu and Norton in 18. So they construct for every vertex, they add a correction term to this part of the smooth end curve that corresponds to the irreducible component associated to this vertex. So you add a correction that is dependent on S to the differential restricted to this component. Such that the resulting differential goes to something holomorphic. And moreover, they should be normalized so that the things you add, they should vanish when you set s equal to 0. And the precise normalization they use is using a symplectic basis. And okay, so they're normalized such that eta vanishes at s equals 0. So this means, so in this case, you have a symplectic basis for the original curve, which now will be taken to be a union of symplectic bases for the various components. Which are identified alpha G, G, beta G, V.
So this eta V is a section, how should I think of it? The section of the bundle?
It is. I will tell you. I will quickly tell you how they construct this. So I mean, they construct this by taking. So you take this error. You take this jump that you want to cancel out, and then you integrate it along some integration kernel called the Cauchy kernel, so that you get some differential that you can add to. You do that for all the curves simultaneously, and you get some differential that you add to all the components, and then you cancel out the jump, but you get some error term that is smaller. But this is smaller in successive, like in higher orders of s. So if you iterate this process and integrate the new jump, you're going to get something else that you can add to try to cancel it out, and then the error will decrease in higher orders of
Can
S.
you use a section of some jet bundle or something?
I think it's just a differential, isn't it?
It's a differential on the complement, like it's going to be a differential for each of these things. So when you sum all of these things up to get, you eventually get something that cancels out the jump completely. So yeah, I mean, I don't know how else to describe it, but it's...
I think the tautological answer to your question is yes, because she's solving a differential equation, and it's kind of that solution is that.
Maybe there is something to mention here. So when this idea goes back 60, 70 years maybe. But the question is, if you look at this, do you want to work on the Riemann surface with boundary, or do you want to work on a closed Riemann surface? And if you work on a Riemann surface with boundary, then algebraic geometry language is a little lacking. And also, you need to then decide how whatever you construct is going to vary based on the boundary. So somehow this trick is a trick to work on a closed Riemann surface, on the components. And then this is algebra geometric. Sorry.
Yeah, thank you. Thanks. Yeah, thank you. Yeah, I mean, Sam Gruszewski knows a lot about this. You can also ask him.
Sorry.
Okay, so this basis can also be viewed now as a homology basis for the smooth end curve by just taking the same cycles. And then we require the normalization. That's they integrate to 0 over the alpha cycles. Okay, so now I already told you now how we construct these differentials. So now let's try to Taylor expand the Torelli map.
So somehow all of the analytic properties then reduce to understanding this eta.
Yeah, exactly. So first you expand eta, and then you integrate to get an expansion. Because of some like uniform convergence, you can also get an expansion for the integrals, and that's for the period matrix.
But just to understand, so you construct this eta term by term, and then somehow you prove convergence.
I don't know exactly how the convergence. Well, yeah, exactly. That's how you do. Yes. So you first integrate once, and then you integrate again, and then you add the things up together, and you get some Taylor expansion in the smoothing parameters. Because since the jump decreases by like higher order of S all the time, and then you have to prove some convergence, which is done in this paper.
And you have to prove it uniformly in the X parameters too somehow.
Yeah, I mean in the X parameters. Yeah, I mean it's like these are not the difficult part of the question, because like everything is like just varies holomorphically there.
So in that paper, Hu and Morton, there's some kind of formula for these perturbations, the correction term.
Yeah, or I mean they don't write them out completely, but they write some first order term for. I mean they have a method for computing them completely for all of these separate things that you add together. But then you also have to like. I mean then you have to like write out what the actual full expansion is, which I mean you can also do from this paper and just a bit of like reform like analyzing the proofs there, for instance. Okay, so first I need to introduce some object that will appear in the expansion. So for a smooth curve, I denote it now by C prime. We have an object called the fundamental bidifferential, or also known as the Bergman kernel. or it can also be seen as some function or some bidifferential in the local coordinates near to or some local coordinates. And okay, so it's the fundamental bidifferential. And it's characterized by a set of properties. Okay, we also require it to be normalized so that it's uniquely defined. So what is it? It is some bidifferential in P and Q, so you have some monomorphic function in P and Q, and then times dP dQ, where these are differentials, such that the only pole of this F occurs in P equals Q, and then we have a pole of
Sorry, so this is now P and Q are varying points?
Yeah, I mean, yes,
So
yes,
you have a
exactly.
section on C prime cross C prime.
You have a section on C of something. Yeah, probably. I don't know.
Omega
What?
squared.
Yes. Okay. Yeah. I mean, yeah. It's maybe it's nice to actually write down like this lies in something, but
It's called a bidifferential.
but I mean, from this description, you should at least be able to see what it is. So okay. So here F minus this part is holomorphic. And it's symmetric in both arguments. And it's normalized so that the integrals over the alpha cycles vanish. Okay, so that was the object I wanted to introduce. And now, when we expand the period matrix, we first note that the period matrix now can be decomposed into various blocks. For each pair of vertices in the dual graph that correspond to pairs of positive genus, you get a corresponding block in the period matrix that corresponds to integrals of differentials that are varied differentials from a basis of one of the curves over a homology basis for the other curve. So when s equals 0, and the vertices are not equal, these integrals will just be 0. But when you smoothen the curve, you will get something. You vary the differential, and then you will get something that is non-zero. So let's see if CV prime be irreducible components of C, and the genus is greater than 0 because otherwise the block will just be trivial, or there will be a 0 by 0 block. So we let mu associated to beta prime be the basis of varied differentials on CS that extend the basis of holomorphic differentials on C. Or on CV prime. Okay, so then if you combine the proofs, in Norton and in this paper by here in Norton, and in an earlier paper by Yamada, you can obtain a Taylor expansion for each period matrix entry.
So maybe you said the varying differentials are varied holomorphically in the X and S.
Yes, yes, yes. Okay, so this is the complete Taylor expansion in the S variables. So first you sum over the paths between the vertices V and V prime. And then you sum over some exponents of the smoothing parameters, I1 up to IR, where these I are greater than 0 and R is greater than or equal to 1. And then, okay, so you have some coefficient times the smoothing parameters raised to these choice of powers. And the coefficients, first, it will be a product of, first you take the holomorphic differential dual to on V, that is dual to alpha j, and you differentiate it, sorry for a lot of notation, but you differentiate it I1 minus 1 times, and you evaluate it at the node QE1, so the first node along this path. And then you take the differential which you varied and integrate it here, so this differential when s equals 0, and you it's on V prime, and you differentiate it IR minus 1 times and evaluate Q minus ER. And then you have some constant, or some coefficient that is dependent on this I and on the curves along this path. So this coefficient is an explicit constant. So I can also find exactly what it is. Oh, it's an explicit constant dependent on the coefficient. And dependent on the holomorphic parts of the fundamental bidifferentials of the curves along this path. And their derivatives. And their derivatives will be of orders like ij minus 1 in one entry, and then ij plus 1 minus 1 in the second entry.
But could you locate this entry in the diagram?
So this will be it will be an entry that corresponds to the block. Like you have a period matrix, and then you have a block here that corresponds to integrals of holomorphic differentials of one curve over homology cycles of another curve. So all the block diagonal. So the diagonal entries will be the block diagonal will be integrals of differentials on the same curve over cycles on the same curve, but when you go off diagonal, you get.
Yeah, but then don't you need like two indices there, like V prime, not just V prime, or what?
This V prime, here's V.
Ah, the V's there.
Yeah, yeah. Okay. So
and these two and the subscripts there for one is for one of the cycles on. I mean, there's an I, and what's the other thing? I.
J.
So you take the basis on.
Yeah, you take a basis and vary it, and you take a basis. I also got S here, but it's the same as Moduli.
Sorry, I have a stupid question. So why is this thing a number? Is it a number? It's like you
Okay,
take
so if you take the differential values, I mean, I disregarded part of D.
Yeah.
Z, so it's going to be
Oh,
a number.
I
And
see.
you evaluate it, so it's going to be a number.
That second subscript is an S underline, or what? I'm just trying to understand the notation.
Yes,
Okay.
because you vary the differentials.
those are like, yeah, it's a number when you put it
So
in
it's a
there.
number, but if you vary the nodes, you get a function in the x variables. I equals 1, 2.
Everything in the under bracket is a function of x variables, right? Or, yeah.
Everything in the under bracket.
I mean, this thing you've under bracketed, under brace.
Here,
Yeah.
yes, everything, not this part.
Yeah.
Yeah, exactly.
This formula is actually the heart of the matter.
Exactly. So this is what allows us to do computations. And so now, okay, it's pretty. Okay, so now now that you have this Taylor expansion, you can technically compute the scheme structure of both the fiber products of the set fiber product of the Torelli map and of the Torelli map and the product map. But I computed the full structure in case B, whereas in case A, and also you can obtain a similar expansion for cases in the boundary of the prim map. But for the cases A and C, I did it in some cases where you have where you only have a few, like 1 or 2 nodes or so, because otherwise you get a complicated system of equations that I don't get.
Let me just understand that once you pick V and V prime, then there's a unique path.
Once you pick V, yeah, there's a unique, yeah.
How do you put a sum there?
I mean, no, okay, there's a unique shortest paths, but you can also go back and forth.
Oh, yes.
Okay. Okay, so and in the case B, the fiber product turns out to be reduced, whereas in the other cases that I computed, you get non-reducedness both in the prim fiber product and in the cell fiber product of the Torelli map.
So, in terms of the non-reduced situation, you're just going to tell, like, you're saying what happens is some low degree term is like just a square, and you see that quickly, or?
Yeah, I mean, yes. So I mean, this will depend on like the order of vanishings of these derivatives of differentials evaluated at the nodes.
So what is the simplest case where you get this non-reduced? Where we can.
For instance, if you take the self-fiber product of the Torelli map in genus 4 and you take 2 curves that are glued together at points that are equal, and then you're gonna get equations, and then you take 2 differentials that are units at these points, and then you're gonna get some coefficient in front of the S2 term that is the derivative of this differential. Wait, give me a second. No, yeah, wait. Yeah, I think if it's the curves are not hyperelliptic, then you can pick derivatives. Okay, okay. I mean, I don't know. I don't remember exactly, but I mean, I can't do the combination now, but I can show you afterwards. But
so I take the same curve of genus 4 twice, and I take the diagonal, so to say.
Yes, but also, I mean, this is not an element in the fiber, or I mean, an element in the fiber product will correspond to a pair of 2 curves and the choice of isomorphisms of the Jacobians. And when you take the isomorphisms to be like identity on the lower and minus on the other, you get some stack issue and you get some fiber product of 2 slightly different maps. But you're going to get equations where you get so this smoothing parameter is S and this is S prime. So you're going to get something where you get the equation like S squared plus S prime squared equals 0, and S plus S prime is equals 0, and you substitute it here and you get 2S squared equals 0 and then S equals 0. And plus some other terms that you cancel out by Nakayama or something like that. But yeah, so this is the simplest case. But let's now move to the best case where we don't have non-reducedness, which is the case B. B, and this is the fiber product of the Torelli map with the product map. So a point for this fiber product, since we're considering a fiber product of stacks, we have to pick a point here and a point here and a choice of isomorphisms of their images in AG. So a point will correspond to a triple of a curve and a tuple of k abelian varieties and a choice of isomorphism between the product of Jacobians of the irreducible components of the curve and the product of these abelian varieties. And this isomorphism is essentially determined by where these separate, to which factor these separate irreducible components go because of the indecomposability of principally polarized abelian varieties. So the scheme structure here is going to be the quotient okay, the first variables corresponding to MG compact type, and then the variables corresponding to this product locus. So we have the coordinates x and s, there are coordinates for MG compact type, and then we have x1 up to xk that are coordinates for these smaller Siegel upper half spaces by an ideal okay, so you wanna, so essentially to get, since you're taking the tensor product of two very explicit maps in local coordinates, you get the ideal of relations by setting the matrix entry of the Torelli map equal to the matrix entry of the product map. So essentially, if you're looking at the blocks, that correspond to smaller Siegel upper half spaces, then these blocks, when you set them equal to whatever you get from the Torelli map, you're just going to eliminate the variables that correspond to smaller Siegel upper half spaces. So it's only the off-diagonal blocks that are interesting to us. And these off-diagonal blocks, okay, so first you set xi equal to the off-diagonal block. Block of size gi of the period matrix SS, and then so the off-diagonal blocks will correspond to integrals of holomorphic differentials in one curve over a homology basis of another curve, where these curves have Jacobians that land in different factors under the isomorphism of the product of Jacobians and the factors. So if we let E1 up to ER be the shortest path between V and V prime in dual graph, then we obtain, by looking at this Taylor expansion, actually in this case we don't need the full Taylor expansion, but we only need the terms of lowest order. So then the integral over this very differential of V prime over cycle of V will be divisible by this product SE1 up to SER times some coefficient. And this coefficient can be is a unit in some cases. So when you take differentials, which you can always do because of base point freeness of the canonical system. This Vj should evaluate to something non-zero at V1, and the Vi on the other curve should evaluate to something non-zero on QE minus R. And then we also require that the curves in the path that are not equal to V and V prime should all have genus 0. So then we obtain the coordinate ring that is given by only now the variables, power series in the variables of the model space of curves, and then divided by a set of monomials in the smoothing parameters along paths that I won't write this out, but P sigma is now a collection of paths. P is a set of paths. In the dual graph, such that the n vertices of this path should have positive genus, and the interior vertices of the path should have genus 0, and the Jacobians associated to the curves v and v prime that are n vertices of the path should land in different factors under the isomorphism of the Jacobian and the product of the abelian varieties. So, more questions?
These are now all simple paths.
Oh yeah, and also because now, yeah, so these variables are not repeated, so you get a square-free, you get an ideal generated by square-free monomials, and then by commutative algebra exercises is reduced.
So the examples you've drawn, you've mostly had just two vertices, and then this condition, then there's no intermediate vertices. So this is all automatic.
Yeah, exactly. But in the general case, like for all curves that are separated, like you can always find like a subpath that consists of curves that are only separated by genus 0, and then that will vanish, so the whole thing will also vanish. For curves that have Jacobians and land in different components, and that's more busy.
So your coordinate ring, it's this power series ring quotiented by a product of SEs. I'm sorry, so the SEs are power series in the variables S or X given by the expression?
Oh, sorry. Wait, and for the x's, yeah, no, nothing in the x's.
I mean, the SEs are not, so your variables S are also indexed by edges of the graph.
Yeah.
But
The smoothing parameters.
so this is just literally saying if the path only has one edge, then it's just you quotient by that thing, and that's the coordinate. Okay.
Yeah, exactly. Yeah. And okay, so this is saying that, I mean, for this to be 0, this means that you can't, if you have two curves, so Jacobians land in different factors under this isomorphism, you can't smoothen out all the nodes here in between and still remain in the product locus, which you would be able to do if these land in the same factor. So this is what the equations are saying. Okay, so now let's move, so as a curio, I'll also talk a bit about PC. So then we have the fiber product of the extended prim map and the product map. And for those of you who haven't yet met or haven't recently seen prim varieties associated to nodal curves, which some of you might not because they don't like to spend so much time in the center, I will briefly introduce them now. So in RG tilde, this is a partial compactification of RG. RG just parameterizes the Tal double covers of smooth curves, but now we allow the curves to be nodal, and this double cover should be induced. So, okay, so this is not a compactification, but it's making this map proper. And so this double cover is induced by an evolution such that the fixed locus of this involution are nodes of C tilde, and there are no at a fixed node, the two branches are not interchanged. And the number of components interchanged should be the same as the number of nodes interchanged. And then the prim variety associated to this double cover will now be, again, as usual, it will be the kernel. First, you take the kernel of the norm map between Jacobians. The norm map is induced by taking a line bundle associated to a Cartier divisor and that leads to its line bundle associated to its image And we take the connected component containing identity, and that's why I put a little circle here. So the first question is now how we find prime varieties that decompose into a product. So there are three main ways that the prime variety can decompose into a product. And already, if we're working in this smooth locus, so locus of double covers of smooth curves, we can already have primes that decompose into a product. And this is precisely where you have a smooth hyperelliptic curve. And you take its set of vice-versa points, P1 of the 2G plus 2. And you divide this set of vice-versa points into two sets. They're non-empty and of even cardinality. And you create two new hyperelliptic curves, C1 and C2, that are ramified along their respective subsets. So the way you get the double cover is that you take the hyperelliptic map to P1, and then you take the hyperelliptic maps for C1 and C2, and you take the fiber product of C1 and C2 over P1, and you get a double cover, a tall double cover over C. And the prime variety in this case will decompose as a product of the Jacobians of C1 and C2. So if these sets have bigger cardinality than 2, then you're going to get two non-trivial factors.
So this is one instance.
This is one instance where you can get a product. There are other ones, and I'm going to talk about them now. So this was the instance in the smooth locus. Okay, so the second case, or the second category of cases, comes from when you have now double cover of the nodal curve. We have two components that are glued together at 2 points, and it maps to another curve. Glued at 2 points, and now this map is 2 to 1. This is C prime, and this is C, and it's 2 to 1, and it's ramified at the nodes. So if I denote this component by, say, or I denote these components by A and B, then the prime variety in this case is decomposed as the product of the primes of. So first you take this separate double cover and glue together the points, and you get a prime variety of this double cover, and then you do the same for the other part, and then this prime variety is going to be the product of these prime varieties. And the third case is when you have instead, so these components will both fixed under the involution, but you can also have components that are interchanged. So you have some part here, or possibly empty, but you have a part here that is fixed, that I denote by B, and then you have this part A that has an étale double cover over it. And then the prime variety of this curve C decomposes as a product of the prime of the fixed part and the Jacobian of the interchanged part. And to get, so these were some cases where you can get two factors, but to get more factors, you take essentially combinations or specializations of these three cases. case study. I mean, it's gonna be a bit tricky when you combine all of these cases, but it's still, I mean, in this way, knowing all of the cases it can decompose into a product, we can now classify all the points of this all the geometric points of this file product, because first you decompose your prim cover by splitting up everywhere where you have these kind of nodes that separates it, and there's an exchange part, and then you separate at these, like, it's called biceps in some paper by Sigran. You separate all the biceps, and then you also take into account whether the curves are hyperelliptic or not, and then you distribute all these factors into.
On the smooth locus, is it clear that this is the only construction?
It is
That leads
proven.
to. It is proven.
It is proven. Clear? I don't know.
By Zidran.
No.
This is like your
Mumford, maybe?
the singularities of the theta divisor.
That is product is the premise product of Jacobi.
Because you have to have a highly singular theta divisor. So this basically rules out a lot of cases.
Okay, so I write something higher. Okay, so in these three cases, for 1 to 3. In these cases, the prim map can also be described now as a period matrix, where you take a double cover of a curve and you associate to it its period matrix that is given by some integrals of some differentials over some cycles, J. And now these cycles will form a basis of the differentials of C tilde that are anti-invariant under the evolution, meaning that they pull back to minus themselves. And then we have some cycles that are anti-invariant in the same way. And they are constructed in a particular way using part of a basis for a C prime that have a C tilde that have some symplectic intersection matrix. So in these cases, actually in this case, when we look at the scheme structure in the fiber product, we don't need to consider the pre-map at the boundary because we're not even working at the boundary. Instead, it's enough to look at the co-differential of the pre-map and show that this is injective on the locus normal to the hyperelliptic prims of hyperelliptic curves, and it injects into the normal of the product locus inside the space AG, and this will prove that it's reduced along the points corresponding to curves in double curves of curves in this case. Whereas if you move to the boundary, we're going to get some non-reduced loci in both cases 2 and 3, and this you can study using expansions of the period matrix. So then what you do is you vary differentials on C prime so that you get a Taylor expansion for the free map. And then to be able to study the coefficients, you would like to know how you can describe the space. And in these cases, it turns out that this space can be described in terms of linear systems on the curve, on components of the downstairs curve C. Of C, analyze the coefficients. And obtain equations. So you're going to have to analyze when they are base form free or separates the various nodes and to what order of vanishings they have at the nodes. Will all be relevant when you study the equations. there's a lot of interesting geometry going on there, but which I'm happy to talk about with anyone who is interested. But I will finish my talk here.
Questions?
Yes, so for this last, so what intersection theoretically result you prove with this Taylor analysis of the free map?
I haven't been able to prove any intersection.
But what would you like to? What's the aim?
The ideal thing, which already is a bit complicated, would be to find a way of computing the prim pullback of the product locus. In the tautological ring of RG tilde, which is also a bit under construction, or would you say it's?
That's not the worst problem.
Yeah.
I mean, in principle, if you computed a local structure in every issue here, you could try to compute it, but it's going to be hard. It's going to be hard work.
Yeah. So we're not sure if it's actually, maybe it's not worth like trying to carrying out this computation now, but
maybe if as I say, maybe if Gabi didn't understand that you told him the exact point where it's not reduced in the first case, A.
I understand.
So for Torelli, you got monomial equations.
yeah.
What happens? What kind of equations?
So in the proof map, you can get equations of the type like, I don't know, like x, s, comma, s squared. So you have some like, so there are some nodes that, sorry?
That's the monomial.
Oh, yeah, sorry, monomial, yes, monomial. It's monomials, but it's like you can have squares, it's no longer reduced. In all the cases, I have also obtained monomials. No, wait, no, it's not, no, wait, give me a second.
You don't have to answer immediately.
No. No, I can also get differences of monomials. Because if you have two curves that are glued together at 2 points, you have some parameter here, s and some s prime, and you have some parameter x and x prime. You can get maybe some like x, s minus. I mean, you can get like differences of monomials too, so not necessarily only monomials.
And so what?
So differences of monomials are still binomials. So
Yeah.
there's some
you get
toric structure.
you get sums of two monomials.
That's the hope to do any this intersection theory calculation. You hope that you just get something toric. Otherwise, no way.
But so what if you, so here you have a good starting point because you have this Mumford theorem that indeed on the smooth locus you have its clarity, what is the...
Yeah.
But if so, you have still, I guess, for to take when is the primal Jacobian, yeah? They have this trigonal construction.
Yeah, but...
But
it's a Jacobian, but it's, I mean...
No, but you still have at least a geometric understanding of the situation on the smooth locus. So maybe that's the pullback of...
I mean, I have a complete, the complete geometric understanding here, because I mean, you're looking for products, and products can come either from the boundary, because you separate components, or, so I mean, first you do all of this, and then you look at, so I mean, see, because of indecomposability, you can first like just split up all the possible ways from the boundary, and then when you can't split up anymore, then if it's hyperelliptic, which is a specialization of this case 1, you can have a product of abelian varieties. And in no other case, I mean, if you can find another way it can decompose, it will also be, you can also describe it in terms of specializations of these cases. So if you get a Jacobian from a trigonal construction, if the Jacobian decomposes as a product of abelian varieties, it will mean that you might have several irreducible components of the curves. So you probably have some nodal curve, and then you can probably apply some of these cases to split it off. So otherwise you probably get the Jacobian of a smooth curve. If you have a smooth trigonal curve.
If you just go back to the Torelli example, can you say anything about the beyond compact type?
Yeah, if you compactify, you can try to. Okay, so I mean, I did also the computation for M4 bar, but in general, like you would have to. So in this case, we could like ignore some cases of like low codimension because of the particular dimensions in this case. But in general, I mean, you can also, I think it's very possible by, I mean, maybe you instead consider period matrices with less rank or something like that, and you take the fiber products, and it should probably be very similar.
Would you have similarly so you lend heavily on this Hu and Norton description?
Yeah, so they can vary, so I mean, you can vary differentials on any stable curve, but I think that if you look at differentials that, I mean, if you look at the differentials that you want to vary and integrate of some other curves, I think that the only thing that matters are like cycles that don't, I mean, if you have some curve that looks like this, like the differentials in cycles don't be those that go to nodes, but you have set of components or something like that, and so then you get all the nice convergence results that you have for a compact type. Probably. I haven't done the computation, but I would expect this is the case.
So I think maybe this was Gabi's question, but there's two kind of open subsets that are suggested by this 1, 2, 3. The first is that you just restrict to RG,
Yeah.
and then you just do that pullback.
Yeah.
And
So this is only considering.
yeah. So is that thing is nice or?
That's nice. That's completely reduced.
And then the other one is that you remove the closure of the hyperelliptic locus. And then only consider these types of products.
Now here I only say even 2 nodes. I don't even say that I can have more nodes by specializing. But I mean, if you want to obtain more factors, you have to allow for.
Sure, but like
But
so.
So if you specialize, it's of course still gonna decompose as.
But the bad structure happens immediately in 2 and 3. You don't need.
Immediately here, yeah, immediately.
You don't need to intersect with 1 to get to that.
I think maybe in this case, like at least you get something bad in the intersection of this with the specialization of the hyperelliptic.
So that's what I'm curious about. Is if you remove the closure of the hyperelliptic locus, maybe this could be nice.
So here, I think it's also not nice if like maybe not the whole bit is hyperelliptic, but only B is hyperelliptic, or maybe in this case also where only 1 is hyperelliptic and you do it at points. So it's not exactly.
Thanks. Any more questions?
So about a more basic question. So this Bergman kernel and alpha integrals, beta integrals, is there a way of algebraizing this and having these bundles on some, I don't know, some log structure and have churn classes of these bundles?
Tell me.
Did you guys write a paper on AG with the heat calculus?
That could be nice. You don't like complex analysis.
I mean, I would guess that, I mean, even if you, somehow at some point you have to show that something doesn't vanish, right? And that's how they get the transverse intersections. And that,
Yeah, but what does that mean algebrogeometrically?
okay, I mean, I would be like, my guess would be that you can make a formalism, but then the proving the non-vanishing is probably.
Well, then proving the thing, of course, you will get back to what you have. But,
Okay, yeah.
You think that your new formalism might even work
But
like
you could have
calculus?
intersection numbers, and right? I mean, the first talk went into this direction of algebraization of, yeah.
But it's a local coordinate, like how do you imagine?
Yeah, that's the right.
Well, I think it should be related to the second fundamental form.
Yeah.
Yeah, maybe.
But
Maybe.
it is still, that is still
Yeah.
differential geometry.
Maybe, yeah. I'm not
No,
entirely
but
sure.
still, they interpret it as a
unique
section,
yeah.
like as a form on C times C with
Yeah,
poles.
it could be that you can do it.
No, so I think that there was this definition of this Bergman kernel. Yeah, so that is can be characterized as a unique section on the symmetric product of the curve with certain conditions.
Yes, yes.
Yeah, but that's just the unique section of the canonical box, canonical twisted by minus twice the diagonal. That's
Right.
it.
Yeah,
That's what it is. That's an
that's
algebraic
what-
object.
and that
Yeah.
can-
There is a way to write it explicitly. I mean, you need to normalize it to say the bi-raised to whatever along the diagonal is standard, but that's all. And that's an algebraic object. There's a second fundamental form.
Yeah,
So,
okay. Yeah, okay. So you mean it's not, there is some, it's not an holomorphic variable.
No, that's not
Yeah,
holomorphic.
that was.
So that's-
Any last few questions? All right, thank you. Thank you again.